In this video, we will find the volume of a shape when given the base and the shape of its cross sections. So the problem says find the volume of a solid whose base is the region D between y equals the square root of 4 minus x squared and the x-axis, and the cross sections perpendicular to the y-axis are isosceles right triangles with hypotenuse on D. So let's begin by drawing a picture of the region D. So I'm going to draw some axes. So when it says that we have the solid whose base is the region D, that means D is sort of the bottom of this solid. So the square root graph, this is a semicircle. Its center is at the origin. The radius is going to be 2. Okay, so we're going to draw a semicircle. This is 2. This is negative 2 on the x-axis, and this is positive 2 on the y-axis. Okay, so the region between that semicircle and the x-axis, that is the base of the solid, the bottom of the solid. So above that, it talks about cross-sections, the ones perpendicular to the y-axis, are going to be in the shape of isosceles right triangles. Okay, so an isosceles right triangle is something like, I have a triangle, it's a right angle triangle. And for it to be isosceles, that means that two of the sides have to be the same. The only way that could happen is if these two legs of the right triangle are equal. Okay, but this problem says they're isosceles right triangles with their hypotenuse. The hypotenuse is on D. So the hypotenuse needs to be on this base. So instead of looking like that, our triangle is going to be more like, will look like this, where the hypotenuse is going to be on that base, and our triangle will be oriented more like this. So I'm going to draw one such cross section. Okay, so its hypotenuse has got to stretch all the way across that base, and then extending up out of the page are going to be these two legs. So I'll do my best to try to make it look sort of 3D, but it's going to be tough. Okay, so I have something like this, and here's my right angle. I'm trying to draw that tip sort of slightly offset from the y-axis to make it look a little bit more 3D. It turns out if you draw it right above the y-axis, it looks less 3D. Okay, and then this cross-section has to have some thickness. Okay, so that thickness will extend in the y direction. So even here, there's some thickness. So this triangular wedge. Okay, so this is a 90-degree angle where the right angle is. The other two are going to be 45. So 45-degree angle. So even in this smaller picture, this is a 45-degree angle. That's a 45-degree angle. All right, so if I use my volume formula, our volume is going to be the integral. And my thickness here, the thickness is in the y direction. I'll write a dy. So we will have a dy integral. So I need to write the area of this cross-section as a function of y. And the y values will start here at 0, and they extend up until I reach y equals 2. All right, so I need to be able to write down the formula for the area of this cross-section, this triangle. Okay, so let's say that the length of the hypotenuse is c. Using 45, 45, 90 stuff from geometry, or if I use Pythagorean theorem, the leg is the hypotenuse divided by square root of 2, as will this one. Because in an isosceles triangle, the two sides that are the same length, oh yeah, they're the same length, so they're both c over square root of 2. Okay, so I could get that using, again, 45, 45, 90 from geometry or Pythagorean theorem. Okay, so with that said, I can now write down my area. It's going to be 1/2 base times height. So c root 2 times c root 2. And if I give myself more room, this becomes 1/2 times c squared over 2, which is c squared over 4. All right, so we'll get the integral from 0 to 2. It'll be a dy thing. And the area is going to be c squared over 4, where c is how long the hypotenuse is. Except I don't want to write I don't want to keep c there because I need my variable to be y. So let's see if we can find the length of this hypotenuse using the picture. So this point over here, I'm going to call x comma y. Okay, and based off of that, the length from this center point to this point, that length would be x. And by the symmetry of the picture, then the whole hypotenuse would be 2x. So 2x, that is c. All right, and if we plug that in for c, we will get 2x. We'll get 2x being squared over 4. And I can simplify and I get the integral from 0 to 2. This will become just x squared dy if I were to simplify. Okay, but right now the variables don't match up. So what I'm going to remember is I know the equation for this point. I know the equation of the curve that this point lies on. So I'm going to use that semicircle equation. Y equals square root of 4 minus x squared. And I'm going to isolate y to plug in for the x here. So if I square both sides, we get y squared equals 4 minus x squared. If I rearrange this, we get x squared equals 4 minus y squared. And if we square root, we'll get x equals the square root of 4 minus y squared. Technically, we'd have a plus or minus. But looking at where we labeled our point x comma y, our x coordinate is definitely non-negative. Our x coordinate where we drew it is non-negative. So we would put no plus or minus here. We just keep the positive version. All right, and now if I plug in, we get the integral from 0 to 2. Our x is the square root of 4 minus y squared, and that is being squared, dy. And from here, it's not bad. We get the integral from 0 to 2. When I square this, we get 4 minus y squared, dy. The integral goes away. Sorry, the square root goes away. Now we can take the antiderivative, which is 4y minus y to the third over 3. Got to plug in the 0 and the 2. If I plug in 2 into this, we'll get 8 minus 8 thirds. And then minus, if we plug in 0, you'll get 0 minus 0. And if you get a common denominator, this will end up being 16 over 3. And that's our answer. That is this volume. So in terms of our goals for this section, I forgot to mention at the end of the last video, but we talked about how to find the volume of when our shapes are volumes of revolution. And in this video, we discussed how to find volume of solids where we know the base, the bottom, and we know the shape of our cross sections.